Well, the basic model on which the diagnosis of leukemia and lymphoma was based was almost fully formed by the mid to early 1990s, but has moved on a great deal since then. The model, as it stood at that point and still does, involves comparing leukemia and lymphoma cells with their normal counterparts, with identifying the genetic abnormalities which are present in those cells, and using that as the basis of diagnosis and prognostic information for patients. But two big things happened subsequent to that which changed the field, and both of them are to do with the way that information is processed and handled. And the first was the necessity to bring together all these results of disparate investigations, the PCR investigations, immunocytochemistry and so on, into one composite process for diagnosis. And that's one of the things that we have done a great deal of work on here in Leeds, having a single laboratory which can carry out all of these tests to make sure that the results are internally consistent and that things change with time. The alternative model is that tests get done in individual departments and tend to get locked into the department priorities rather than to do with the diagnosis for the patient. The much bigger change which happened was the ability to do tests in parallel and to look at patterns of results rather than individual results. And that really began with flow cytometry, which is a technique where cells go through a counter. They're tagged with fluorescent antibodies, monoclonal antibodies. And when that started, it was just a single antibody which was added to the cocktail of cells to see which cells expressed that protein. Now you can do 6 or 8 different antibodies at the same time, and you're really looking at patterns rather than whether one single molecule is present or not. That developed in a much wider sense in the molecular diagnostic arena, where using chip-based technology and the new generation of DNA sequencers, it became possible to really extract huge amounts of information from a small sample. So it was possible, for example, to look at the expression of every single known gene, not just the presence of one gene. And again, the output of that is looking at patterns of expression rather than just the presence of one marker or another. The final iteration of that really is in the National Genome Project, where it is now entirely feasible to not just look at the configuration of a single gene, but to sequence the whole genome in real time as part of the diagnostic process for an individual patient. And that's having a huge impact on diagnosis.